In this video, we're going to look at how to find points of inflection and concativity within a function through an extended example. So we're given the function f of x equals 3x to the 4 minus 16x cubed plus 24x squared minus 9. And we're asked for several things. First of all, we're asked to find and classify the stationary points and any points of inflection. Then give the ranges where the function is concave upwards and concave downwards. And finally, hence sketch the graph of y equals f of x. So first of all, let's find the stationary points. To find the stationary points, we have to find f dashed of x, which in this case is 12x cubed minus 48x squared plus 48x, and the 9 disappears when we differentiate it, and let's just factorize that to start with, because we're going to need to factorize it later anyway. That's 12x and then x squared minus 4x plus 4, which factorizes further to 12x, and then that quadratic factorizes into two brackets, which is x minus 2, x minus 2, or x minus 2 squared, we could have written that. Next, we're going to look at how to find the stationary points. So to find the stationary point, we need f dashed of x to be equal to 0. So to find stationary points, we need f dashed of x to be equal to 0. So we put this whole function equal to 0. We get 0 is equal to 12x x minus 2 all squared. And that tells us that we have two stationary points. So we have stationary points when x equals 0 and when x equals 2. Two stationary points there. That's the x coordinates. We can find the y coordinates. Now remember, to find the y coordinates, we have to use the original function. So we substitute the values in. So when x is 0, we get y is equal to minus 9. And when x is 2, we substitute that in. We get y is equal to 7. Now to classify, we need f double dashed of x. So f double dashed of x, remember this is equal to the derivative of f dashed of x. So that's what we had up above for f dashed of x. We get 36x squared minus 96x plus 48, and that is equal to, if we factorize out, we can factorize out the 12 again, and we get 3x squared minus 8x plus 4, and again we can factorize that quadratic now into two brackets, and we get 3x and x and minus 2 minus 2 is f double dashed factorized. Now we don't need that for the next step, but we might need that factorized form a little bit further down. So to classify, we use f double dashed. So to classify stationary points, we use f double dashed of x. And we use the 2 points that we've just found. So we have f double dashed of 0. When we put 0 into f double dashed, we just get 48, which is bigger than 0. And that implies that the point 0 minus 9, it was bigger than 0, so this is a minimum. And we do the second point, we get f double dashed of 2 as our second x coordinate of a stationary point. We put that in and we get that's equal to 0. And remember, if it's equal to 0, that means we need a sign diagram. So in this case, let's just scroll down a little bit. Get more space. In this case, the sign diagram, we've got 2 is the only one we're interested in. We don't need to worry about the 1. So we've got our x values and our f dashed of x values. And we're going to look at 2, we know it's equal to 0. We take a point either side, 1 and 3. When x is 1, f dashed, now remember this is f dashed, so maybe I should do this in blue here, so we can tell that it's f dashed of x. So in blue, so f dashed is equal to, for 1, we put it into the equation above, and we get a positive number. We get 12 times 1 times by 1 minus 2, which is minus 1, times by 1 minus 2, which is minus 1. So minus 1 times minus 1 is positive. When we put 3 in, all the terms are positive, so we also get a positive. So that means that we have positive, 0, positive, so we've sort of got this shape going on, which means we've got a stationary point of inflection. So that implies that 2, 7 is let's get a bit of extra page here so we can fit this on, a stationary point of inflection. That squeezes in. So that's finding our stationary point, but if we go back to the original question now, we were also asked to find any points of inflection. So that's the stationary points. Let's give ourselves a bit more space. So to find points of inflection, we use f double dashed again. So we're still in green. To find points of inflection, we've already found the stationary one, but there might be a non-stationary point of inflection. Points of inflection. We use f double dashed of x is equal to 0. And this is when it changed from concave up to concave down. So that, if we look back to our f double dashed, we have 0 is equal to 12, and we use the factorised form, was 3x minus 2, x minus 2. And that implies there are points of inflection at x equals 2/3 and x equals 2. We've already seen the one at x equals 2. We saw that that was a stationary point of inflection, and we're going to have to check now, remember, to see if these are actually points of inflection. We're not, like at this point, remember that we think that they are, but we need to double check with a sign diagram. So now we're going to use our sign diagram again. We've got x, and this time we're going to use f double dashed of x. So we are in green this time. And we're going to choose points something to the left of 2/3. 1 is between them, 2 and 3. Okay. And we know that f double dashed is equal to 0 here and here. And if we put the other values into f double dashed of x, put 0 into f double dashed, we get 12 times 3 times by minus 2 times by minus 2, sorry, but the minuses give us a positive. Put the 1 in, and we get 12 times by a negative times by a negative. Sorry, the first one's a positive then, so we get a negative. It's 12 times by 1 times by minus 1, so we get a negative. And then when we put 3 in, we get 12 times by a positive times by a positive, so we get a positive. We can see at both of these we have a change of sign. So both have a change of sign. And that means that they are in point inflections. It implies they are points of inflection. So we already know that 2 was a stationary point of inflection, which means the other one is a non-stationary point of inflection. So that means we have that 2/3, and the y-coordinate, if we scroll all the way back up, we have to put 2/3 into our original red function, and when we put that into there, we get minus 67 over 27, not a very nice fraction there. That's what we get. And that is a non-stationary point of inflection. Now we're going to look at concativity. That was the next thing asked in the question. And concativity, remember, is also using f double dashed. So concave upwards implies that d2y, well, we're using f dashed here, aren't we? Let's not use d2y, let's use f double dashed of x is bigger than 0. We can see from our sign diagram that this is true when x is less than 2/3. So this is, from our sign diagram, x is less than 2/3, but also when it's bigger than 2, when x is bigger than 2. It's concave downwards that's when f double dashed of x is less than 0. And again, we can see that from our sign diagram. In this case, it's negative between the 2 points of inflection. So that's when x is bigger than 2/3, but less than 2. Finally, we were asked to draw a graph, a sketch of this. So let's extend our page a little bit more, and we can draw in some axes here. X and Y axes. And we're going to use all these important points. So let's scroll back up to our stationary points first. So here we found our stationary points. We had, let's use a different colour to highlight these. Use a nice pink, a nice purple. And we can go here. We have 0 minus 9 is a minimum. Here, around here, we have that 2, 7 is a stationary point of inflection. And the final useful point that we just found was here. We have that 2/3 minus 67 over 27 is a non-stationary point of inflection. And we know that they're concave up and down between these points. So let's put on the points that we know first. The first one of those we saw was the minimum at 0, minus 9. So at 0, minus 9, we have a minimum. So that's at minus 9. At our stationary point of inflection was at 2, 7. So 2, 7, a long way up here somewhere, we have a stationary point of inflection. That point there. Stationary point of inflection is 2, 7. And then it's a matter of joining them up. This goes up here. Remember, this is concave upwards the whole way, so it's bending down. It's still concave upwards till here, and then here it starts to turn backwards on itself, and then it goes up again in that way. That's not a particularly fantastic diagram, but we can also see in here the non-station point of inflection, which we just found was 2/3 minus 67 over 27. Now, that shows the shape of the graph. We might want to re-sketch it to show it a bit more, a bit better, of a better sketch, but that will do. It shows the two stationary points and the point of inflection. So remember, to work through an example like this, there's a lot you need to do. dy by dx equals 0 is to find stationary points, or f dashed of x. The second derivative, d2y by dx squared, or f double dashed of x is equal to 0, finds your non-stationary points. If your second derivative at a point is positive, it's concave up, which means that it's a minimum. If f double dashed at a point is negative, it means it's concave down, which means a stationary point would be a maximum. If f double dashed of x is equal to 0, we have a point of inflection possibly, but we need to check with a sign diagram to double check that that actually is a point of inflection.